All right, so hello and welcome. We are going to go through the beginning of section 4.2 together today. So, section 4.2 in chapter 4, collecting data, is about experiments and designing our experiments. So, now that essentially we have our sample, we're going to take that sample and we're going to design the experiment. So, we're going to start off talking about what's called an observational study versus an experiment. So, a sample survey is one kind of an observational study. An observational study sometimes kind of like looks backwards. So it could be called what we say retrospective. We examine data like that already exists. So here's a quick example. If we have like factory workers and we find out later on that the machinery that they have used for some type of amount of time that they've been working has some kind of like, or gives them some kind of exposure to radiation. So we might want to go back and look at the data that we have, like who was working in the factory for how long, who was operating that machinery, and look at that data and see what that, exposure to that radiation has, what effect that has had on the people. um, if you think about it, like if I want to know about the exposure to that radiation and the effects of that, I'm not going to purposely give people that radiation, So we kind of like come to our conclusions and analyze that data based upon something that has already happened. So that's retrospective. On the other hand, we might have an observational study that is prospective. So it kind of like tracks people into the future. So here's a quick example of something that would be a prospective study. So we might want to follow like a group of people who might be, for whatever reason, high risk to contract HIV. So what we're going to do is we're not going to, again, similar to what I was saying, we don't want to necessarily put them in positions where they may or may not get HIV, but we will just kind of track data on them. We're going to, keep track of their lifestyle choices, things that they do over maybe like the course of 5 years or 10 years or whatever. And then we're going to determine, who has gotten HIV and who has not. And we're going to look at that data that we've collected along the way to see, well, do we think that any of those lifestyle choices or whatever it might be make someone more likely or less likely to get HIV? So that's prospective because we kind of like collected our sample from the beginning and then watched them over the course of, however many years. So now let's talk about an observational study versus an experiment. So is taking vitamin D supplement good for you? Hundreds of observational studies have looked at the relationship between vitamin D concentration and various health outcomes. So an observational study is one where we observe individuals and we measure variables of interest, but we haven't actually influenced the response. We haven't imposed a treatment. And that's going to be like the terminology that I think is most important. Is a treatment imposed? Did we give them vitamin D? Did we tell these people to take vitamin D or a certain type or a certain amount of vitamin D or not? If we didn't, if we just kind of like observed what they did and observed, the outcomes, then that's an observational study. So a response variable is the outcome of the study. An explanatory variable may help explain or predict changes in the response variable, kind of like X and Y, like what we think of traditionally. So unfortunately, it's really difficult to show cause and effect. We talked about this earlier in the year. So from an observational study, it's really hard to show cause and effect, okay? So if we want to show cause and effect, we want to run an experiment. But here's just another look at why. So why is it hard to kind of draw a conclusion, a cause and effect conclusion? Well, if I'm just doing an observational study, okay, if I'm just doing an observational study, I might look at people who have high amounts of vitamin D, and then people who have low amounts of vitamin D, and maybe I want my response variable to be how likely are they to have diabetes. So that's the response variable I'm trying to measure. Well, there's other things that kind of go along with, you know, predicting whether or not someone has diabetes: their diet, their exercise, whether they take other vitamins or supplements, genetic history, things like that, right? So maybe these people who have high vitamin D concentration in their blood, maybe they just so happen to take a lot of other vitamins. Maybe they just so happen to have a better diet. Maybe that's why they had a higher vitamin D concentration in their blood to begin with. So maybe some of those other things are part of the reason why they're less likely to have diabetes. So that's called confounding, and we've talked about this before too. But it's when two or maybe three or more variables are associated in such a way that we know that these people were less likely to have diabetes. We know that this group of people was more likely to have diabetes. But do we know that it's because these people had a high vitamin D concentration in their blood and these people had a low? Not really. It could have been because of some of these other things. It could have been because of the vitamin D concentration, but we are not really sure. Okay. And again, that's in an observational study. When we didn't actually impose the treatment, we didn't actually tell them to take vitamin D supplements or whatever. So to determine if taking vitamin D actually causes a reduction in diabetes, researchers in Norway performed an experiment. So the researchers randomly assigned 500 people with prediabetes to either take high dose of vitamin D or a placebo. A placebo is a pill that looked exactly like the vitamin D supplement but contains no active ingredient. So in other words, if the vitamin D was like a white pill, the placebo would look exactly like that. It would be the same exact white pill, but it would just be like a sugar pill or whatever. Maybe not a sugar pill, but whatever. It wouldn't contain any active ingredients. So after 5 years, about 40% of the people in each group were diagnosed with diabetes. So an experiment, we are actually deliberately imposing a treatment as opposed to in the observational study. We were just kind of observing. We were just kind of checking things out, studying the data, right? Letting people kind of do their thing and then looking to see what happens. In this experiment, we're actually imposing the treatment. We're giving some people the vitamin D, and then some people we're giving the placebo or no additional vitamin D. So a placebo is a treatment that has no active ingredient but is otherwise like the other treatments. So here's a really good example: this COVID vaccine, right? That was, just approved and is being approved and is still being developed by some other, drug companies. So a placebo sometimes is a pill, like in this vitamin D example, but in the case of like the COVID um, vaccine, the COVID vaccine is a shot as of now, right? It's a shot in the arm, like a flu shot or whatever. So the placebo in this case would be a shot that comes in the same exact like type of vial with the same exact type of needle or whatever, but instead of being like the active ingredient, like the COVID vaccine, it would be like, I don't know, water or, saline solution, whatever it would be. All right, so that would be the placebo. So people think they're getting the COVID vaccine, but they didn't actually. All right, so more about experiments. An experiment is a statistical study in which we actually do something. Again, we impose a treatment to people, and a lot of times we kind of like default, and I as a teacher kind of default to people, but it doesn't have to be people. Animals, trees, potato chips, whatever. Okay, and we want to observe the response. So a specific condition that's applied to the individuals in an experiment is called a treatment. If an experiment has several explanatory variables, a treatment has a combination of specific values of these variables. So for example, your treatment in like the COVID vaccine would be like the COVID vaccine itself or a placebo. An experimental unit is the object to which a treatment is randomly assigned. When the experimental units are humans, they're called subjects. So those people that were in that, you know, the vaccine trials, they were called subjects because they received that COVID vaccine or the placebo. But like I said, if we were doing an experiment on potato chips or on, like, let's say we want to test a certain type of fertilizer and see if the fertilizer, helps like roses grow taller or something like that. The roses are the experimental units, or because they're not people. All right. So let's look at another example. So malaria causes hundreds of thousands of deaths each year, with many of the victims being children. Will regularly screening children for malaria parasite and treating those who test positive reduce the proportion of children who develop the disease? So researchers worked with children in 101 schools in Kenya, randomly assigning half of the schools to receive regular screenings and follow-up treatments, and the remaining schools to receive no regular screening. So children at all 101 schools were then tested for malaria at the end of the study. So first of all, before we get to this question down here, this is an experiment because we are imposing a treatment. The treatment that we're imposing is the regular screenings or not, right? It's not an observational study. So the question is, identify the treatments and the experimental units. So this can be a little bit tricky. The experimental units in this case is actually not the kids. That might be what you first thought. It's the 101 schools, because when we go back up here, it says we worked with children in the 101 schools and we randomly assigned half of the schools to receive regular screenings. So let me go here. The treatments are the regular screenings and the follow-up, or they're getting no screening, right? So those are the treatments, and they tell us that they're randomly assigning half of the schools to receive each. So it's tricky. The experimental units are actually the schools. All right, so here's another one. This one's a yucky one. So researchers from Rutgers University put the 5-second rule to the test. They used 4 different types of food: watermelon, bread with butter, and gummy candy. They dropped the food onto 4 different surfaces: stainless steel, ceramic tile, wood, carpet. They waited for 4 different lengths of time: less than a second, 5 seconds, 30 seconds, and 300 seconds. And then they used bacteria prepared 2 different ways: in a tryptic soy broth, I'm not sure if I'm saying that right, or peptone buffer. Once the bacteria were ready, the researchers spread them out on the different surfaces and started dropping food. So the factors in this experiment and the number of levels of each factor. So again, the factors are like the explanatory variables. That's how I think of it, okay? So when I look at this, the factor is the variable that is manipulated and may cause a change in the response variables. The different values of the factors are called levels. So when I look at this, I have like 4 different types of food. So food, the different types of food is a factor. And how many different types of food am I using? Watermelon, bread with butter, and gummy candy. So 4. So types of food is 1 factor, and I have 4 levels of that factor. But then I have other factors as well. So other explanatory variables, the 4 different surfaces. So the different surfaces, the type of surface, I have 4 levels of that factor. And then I have the amount of time is a whole nother factor. I have 4 levels of that as well, because less than a second, 5 seconds, 30 seconds, 300. And then the method of bacterial prep, 2 levels. It's either this tryptic soy bath broth, or peptone buffer, right? So there's my factors, 1, 2, 3, 4, and the number of levels of each. So here's another example that I'm gonna kind of come back to a couple times. So if I'm testing a new heart medication, so I'm a drug company, I've developed a new heart medication, and I want to do an experiment to determine if my new medication is effective in preventing heart attacks, okay? So good designs of experiments are essential for effective experiments, just as they are for sampling. To see why, let's start with an example of a bad experimental design. So in other words, I could just take my new medication and I could give it to a whole bunch of people, this new medication that I've developed, give it to a whole bunch of people, let's say 500 people. And then I could measure how many people had heart attacks. And I could say, oh, look, I gave my medication to these 500 people and only, 10% of them had heart attacks. So look, it works so well. It prevented heart attacks in, 90% of the people or whatever. So I start with my experimental units. I think I said 500 people. I gave them my new medication and then I measure the response. So how many people had heart attacks? The problem is there's a lot of other variables besides the treatment, besides the medicine that I gave, that potentially confound with taking the new heart attack medication. So there's some other things that could affect whether or not they have the heart attack. So in other words, maybe age, maybe diet, maybe genetic, like history, family history, um, weight, things like that. So this has like its limits. Doesn't really tell me much. So what we want to do is we want to do what's called a comparative experiment with two or more groups. So we're going to kind of talk through this. Essentially, this design of an experiment, this is the design of an experiment. It's super basic and it's not a good one. It's not going to really tell me good information. So how can we make this better? So before we talk about how we're going to make it better, let's talk a little bit more about our experiment. So maybe I think that going along with my new medication that I developed, I think that exercise has a really big role in whether or not someone has a heart attack. All right. So because I think this other variable plays a big role in my response variable that I'm measuring, the incidence of heart attacks, maybe I'm going to keep track of that as well. And I want to use the drug and the level of exercise as my two factors. So now I want to take my new drug, let me call it drug B, and like we said, I want to compare it to something else. Maybe there's an old drug that's on the market that's been developed by another company or even by our company. So maybe I take my new drug and I want to compare it to the old drug. And then I probably also want to compare it to a placebo. So what happens if these people take nothing? And then maybe I want to look at different levels of exercise. So someone who people who exercise not at all, people who have a low amount of exercise, and people who have a moderate amount of exercise. So again, drug and exercise are my factors, and each of these factors each have 3 levels. So because I have 3 levels in each of these, I'm going to have 9 treatments. So I'm going to have the placebo and no exercise. I'm going to have placebo and low exercise, placebo and moderate exercise, right? Then I could have people who take the old drug, drug A, and no exercise, the old drug and low exercise, the old drug and moderate exercise. And then I could have some people who take the new drug and no, the new drug and low, and the new drug and moderate. So these are my 9 treatments that kind of come about from my 2 factors and my 3 levels of each. So essentially what I want to do is I want to run an experiment and I want to figure out kind of like which combination is the most effective. Maybe my new drug and only a low amount of exercise is the most effective for preventing heart attacks. Maybe moderate exercise is actually like too much, but I don't know until I run the experiment. So that's why I have like all these different combinations, which give me the 9 treatments. So before we get into actually designing that experiment, let's talk about what we call the principles of experimental design. So there's some basic principles that we're going to cover. So just to list them briefly so you know what's to come. We're going to talk about comparison. And we've already kind of like hinted at some of these things. Now we're going to kind of like talk about them in a little more detail. So comparison, random assignment, control, and replication. So those are our 4 principles of experimental design. Let's look at each one really closely. So the first principle, comparison. In an experiment, a control group is used to provide a baseline for comparing the effects of the other treatments. So in other words, in my heart medication experiment, I would want to give the placebo to people because I want like a baseline. What happens if they don't take any medication, the old drug or the new drug? What happens if they don't take either? So the problem is I want to make sure that I want to give them something because a placebo, I want to give them something, a placebo, because sometimes, we're going to talk in a second, people think, oh, I'm not getting anything. So that might have an effect on how they react to my experiment. So in all other aspects, the treatment group should be treated exactly the same so that the only difference is the treatments. So in other words, I want those 9 groups, right? We said we have 9 treatments in this example. I want everyone to be treated exactly the same so that when I measure my response variable, if there's a difference, in like the heart attack incidence, that tells me that the difference in the heart attack incidence comes from the treatments that I imposed. So that's kind of what I just covered there. So let me go back to what I was just kind of like talking about with the placebo. So there's something called the placebo effect. So let me give you like kind of a JV example of this. So like when my little kids fall down and, you know, like get a cut or whatever, get a bruise or just a bump, whatever, they cry and they're like, mommy, mommy. And I give them a kiss on the knee or wherever they got hurt, right? Now, is that kiss actually doing anything? No, but magically they're all better. You know, they think that because I gave them a kiss on the knee, I made them all better. That's essentially kind of like I said, a JV example of the placebo effect. So some subjects will respond favorably to a treatment even if it's inactive. So essentially, my kiss on their knee was an inactive treatment, but they respond favorably sometimes to that, right? Another vocab word to know. In a double-blind experiment, neither the subjects nor those who interact with them and measure the response variable know which treatment a subject actually received. So let me jump back to like we were talking about the COVID vaccine. So we know that when they did that testing, that some people got a placebo and some people actually got like the actual vaccine in their shot, right? Well, guess what? Those people all were seen, you know, like they had a doctor or a nurse, whatever, administer that vaccine and kind of like talk to them and collect results. Well, that person who was collecting those results and who actually gave them the shot, they actually didn't know if they were giving the person a placebo. So remember we said it's like water or whatever, just something inactive, or if they were actually giving them the shot with the COVID vaccine. So let's think why does that matter? Why would that be important? Well, you know, if I'm a doctor and I know I'm giving some people the COVID shot, the COVID vaccine, and then some people just like a placebo, just like, you know, whatever, water or whatever, maybe the people who I give the actual COVID vaccine to, maybe I'm like, oh, look at you, like this is so snazzy, you know, you're gonna, you're gonna have like immunity to the COVID or to the COVID virus, whatever, you know. So I might treat my patients differently, um, depending on the treatment that I know that I'm giving them. And then maybe the people who I give the placebo to, I might be like, you know, here's the shot. Hopefully it works. Hopefully. And then how's that going to make the subjects feel? We're kind of like influencing the subjects, you know? And so maybe that influences their reaction. So when possible, experiments are always double-blinded, we call it. In a single-blind experiment, because sometimes it's not possible to double-blind. So in a single-blind experiment, either the subjects don't know what treatment they're receiving, or the people who interact with them and measure the response variable don't know what the subjects are receiving. So like a good example of this would be if we're doing some kind of like a surgery, if we're doing an experiment on whether like some kind of a surgery is effective. Well, I hope the surgeon knows if they're actually doing the surgery or if they're, doing like a fake surgery. I hope that they know because they're going in there and cutting you open or whatever it is. So there's sometimes, that the doctor or whoever kind of has to know what they're doing. It's not just like a shot, where um, you're just kind of like given this, shot or whatever, and you just shoot it into someone's arm. So to you, the doctor, it doesn't matter if you know or not, right? So double blind versus single blind. The default, we would always prefer to do a double blind experiment, but like I said, sometimes that's not possible. If it's not possible, we want a single blind experiment. All right, so our second principle of experimental design is random assignment. So to create roughly equivalent groups at the beginning of an experiment, we use random assignment to determine which experimental units get which treatment. So here's why. So if I have like 9 treatment groups, like we were saying for that like heart medication, if I were to just say, okay, like let me take like 900 subjects, let me put you all in a big room, and then you 100 over here, you go into the one group, and then the next section you go into the other group, and then the next section, the next, et cetera, et cetera. So if I just say like, here, let me take these group of people, maybe those group of people were just so happened to, if they were the first 100 people, maybe they were the first 100 people there. And so maybe they have similar qualities, like they really want to do this, be involved in this experiment. They're determined to like, have good results. So maybe those people who are like more determined and more excited are all in that first group. Well, that's going to affect your outcome, right? So essentially, randomly assigning people to the different treatment groups is going to kind of eliminate that. So instead of saying, you 100 go over here to this group, you 100 go over here to this group, we have all these 900 people in the room, and kind of like, notice I said kind of like, not exactly like, but kind of like taking a simple random sample, I basically randomly select 100 people throughout the room, and they go into one group. And then I randomly select another 100 people throughout the room. They go into another group, et cetera, et cetera. That kind of gives us greater confidence that all of our different groups have, are more like evenly distributed in terms of like having similar qualities. Um, so random assignment means that experimental units are assigned to treatments using a chance process. So let me show you what this kind of looks like. Okay, so here's another example of an experiment. A total of 20 students have agreed to participate in an experiment comparing the effects of caffeinated cola and then caffeine-free cola on pulse rates. So describe how you would randomly assign 10 students to each of the 2 treatments. So we could do this 3 different ways: using 20 identical slips of paper, using technology, aka your calculator, or using table D. Remember our table of random digits. So I'm going through A and B with you just so that you see them, but kind of like what we talked about with like simple random sampling, you're really going to be using table D. So just so you know, option C is the one that we're really going to focus on. I'm going to kind of quickly breeze through these other 2. So what I would do is on 10 slips of paper, I could maybe write the letter A, and then on the remaining 10 slips of paper, write the letter B, right? So I have 10 A's, 10 B's for a total of 20 pieces of paper. Shuffle the slips of paper, or like put them in a hat and mix them all up. Randomly pick one out at a time and hand one slip of paper to each volunteer. Students who get an A get the cola with caffeine. Students who get a B get the cola without caffeine, right? So here I used randomization to divide my 20 students into 2 groups. So now using technology, I would label each student with a different integer from 1 to 20. Then I would use my calculator, or you can use like computer programs, whatever, to randomly generate 10 different integers from 1 to 20. The first 10, those 10 different integers, get the cola with the caffeine. Or I should say, I'm sorry, the students who match up with those 10 different integers get the cola with the caffeine. And then the other 10 get the cola without the caffeine. So again, those two methods, it's good for you to see them. You might see these again, but table D, this is what we're really going to see most of. So this is our table of random digits. So here's what we would do. And again, I said before, you're going to notice that you're going to see some similarities with selecting an SRS in terms of like the labeling and selecting the digits, but there are some differences too. So look, if we want to randomly assign 10 students to 2 different treatment groups, we're going to label each student with a different integer from 0, 1 to 20. So notice every student gets the same number of digits, right? So if I started with like 800 students, they would all get 3 digits. So like 001 to 800, right? Okay. So then we go to a line of table D and we read 2-digit numbers or 2-digit groups moving from left to right. The first 10 different labels between 0, 1, and 20 are going to identify the 10 students who receive the cola with caffeine. The remaining 10 students get the caffeine-free cola. And you're going to ignore groups of digits from 21 to 99 and then 100. So remember we said in class, like just like with selecting an SRS, you could say like the first 10 unique numbers between 0, 1, and 20, and then that kind of satisfies, like we don't need that last sentence there. So again, it's like similar, like these first couple sentences are similar, but instead of like selecting the 10 people and there's our sample, no, we select the 10 people, they go into one group, and then the other 10 people, it's not like we ignore them, they just go into the other group, okay? All right, so we're going to move on to the third principle. So the third principle was control. So in an experiment, we try to control for the presence of other variables, which may make our results null due to confounding on our response variable. So we're trying to control. Control is like kind of like a fancy, I think of it like as a fancy name for like get rid of or like try and eliminate as much as possible those other confounding variables. So we should keep other variables constant for all experimental units. So in other words, after randomly assigning treatments and controlling other variables, the treatment group should be about the same, except for the treatments. Then a difference in the average response must be due to either the treatments themselves or to the random assignment. So here's what this means, essentially. Like, let me go back to the heart medication, okay? So I've taken my 900 subjects, let's say. I have 900 subjects, 9 treatment groups. So first, in order to make the groups kind of like even, so that, remember we said we don't have like groups of similar people. And here's like another example of that. Like maybe I don't want all the 50-year-olds in one group and all the 60-year-olds in another and all the 20-year-olds in another. You know, I want all the groups to have like different ages and things like that. So again, that's why we randomly assigned people to the different groups. So after I randomly assign the people to the different groups, I'm going to then control for other variables. So maybe, remember we said we're going to study, the two variables that we're going to study are the drug that we give them and then the amount of exercise. So I don't want other things to come into play. Other things that might come into play might be like their diet, maybe their other medications or like vitamins or other supplements that they take. So things like that would be the confounding variables, right? So I'm going to make sure that I kind of like control for those things, and I'm going to say, okay, so everyone's in their randomly assigned groups, you're getting your assigned treatment, but I'm going to make sure that you don't take any other supplements, and I'm going to make sure that I give you like a pretty strict diet that you have to follow. So, and I don't mean like go on a diet, like cut out carbs. I mean like the foods you eat are similar, the things you drink are similar. Maybe I'm asking them to get like a similar amount of sleep. So essentially, I'm trying to make them like live this very similar lifestyle, other than the two things that the two factors, right? So the two things that I'm imposing, the drug that they're taking and the exercise. So if everything else is the same, and then at the end of the experiment, I see a difference in the average number of heart attacks, that tells me that I think that that difference had to have been because of the treatment or because of the random assignment. So, um, one thing to note, just because there's going to be a difference, or just because there is a small difference in maybe the average amount of heart attacks, doesn't mean that it's automatically caused by the treatments. And I know it sounds like I'm like contradicting myself, right? What I mean by that is, let me think of this on like a smaller scale. Let's say I have identical twins, okay? Let's say I have identical twin brothers, and I have them, obviously they have the same like genetic background and things like that. But let's say I have them eat exactly the same foods at exactly the same time, and they go to bed at exactly the same time. And let's say I give them the exact same exercises to do. Let's say they even have like the same jobs and like amount of stress. And let's say they even have like similar families, like, kids and spouses and whatever, okay? Just because, and let's say I give them both my new medication, just because they're living essentially like identical lives, that doesn't mean they're both going to have the same outcome. In other words, one brother could have a massive heart attack and the other one could not, right? So just because I do all these things doesn't mean that, you know, I'm trying, essentially I'm trying to even out the playing field as much as possible, but I can't ever get it to be perfect, even with identical twins. So if there's like a small difference between my groups, that may just be because of like random chance. It might not actually be because of the treatments. So I'm looking for a difference in the, you know, in heart attack incidents, but I want that difference to be like big enough. And we're going to revisit that a couple times throughout this chapter and really like throughout the year, that idea of like, well, how big does the difference have to be like big enough? One other just caution slash reminder, be aware of the placebo effect, which is when subjects from a control group respond favorably to a placebo treatment. A control group is totally different than the principal control. So a control group is like a baseline group, right? That's the people getting the sugar pill or the shot that's just water or whatever. So essentially, they're getting like no, the placebo treatment, a non-effective treatment. That's the control group. The principle of design that we call control is when we control for like confounding variables. So we try and like even the playing field. Remember, we said that that's like everyone has similar diets, everyone takes similar supplements or no other supplements. We try to like keep stress levels to be similar, things like that. So control, when we talk about the experimental design, we're kind of controlling the environment in which these people are living their lives or whatever. A control group is the actual treatment that they're taking. So those two things are easily mixed up. All right, last thing, replication. So let me just give you like another quick example. I wouldn't want to like give one person my new drug, one person my old drug, one person my placebo, and then say, oh, the person that had the placebo and the old drug, they both had heart attacks, but this guy who had my new drug, he didn't have a heart attack. Looky, my drug works so well, right? We want to replicate. In other words, we want to make sure that we give these medications, these treatments to a lot of different people. Because kind of like what I was saying with the identical twins, even if I give the identical twins the different medications, everyone's going to have a different reaction. We want to see, or a different outcome, right? A different response variable. So we want to see like what happens in like large groups of people. So we want to see what we call systematic differences in responses to the levels of the factors of the experiment. So we're going to give each treatment to enough experimental units, people, trees, chips, whatever, so that the difference in the effects of the treatments can be distinguished from chance variation just due to random assignment. So, in other words, replication just means use a lot of people or a lot of objects. So, again, replication can't eliminate chance variation. In other words, that goes back, chance variation means like some people, even with identical circumstances, are going to have different outcomes. So that's our chance variation. Replication, none of these things are eliminating chance variation because that would be impossible to make everything perfectly even. But we're trying to reduce the role. So again, we're trying to like level the playing field as much as possible. So we kind of just talked about this. Replication just means use enough subjects or use enough experimental units. All right, so again, just to kind of like recap these 4 principles of experimental design, just so you know, you might be given a situation, an experiment, and the question might be, how does this experiment follow the 4 principles of experimental design, or do they follow the 4 principles? And you're going to have to, number 1, know the 4 principles and be able to identify, does this experimental design, follow these 4 principles. So just a quick recap. Comparison, we want to use, 2 or more different treatment groups. Random assignment, we want to take our subjects or our experimental units, and we want to make sure we randomly assign them to different groups. Control, remember, this is not like the control group that gets the placebo. We're trying to control and level the playing field. We're keeping the other variables the same. So we're giving them the same diet, we're giving them the same supplements, we're having them sleep the same amount, right? It's not the control group taking the placebo. And then replication, we need to make sure we're using enough experimental units. All right, so in a completely randomized design, so now we're going to talk about a specific type of design. We're going to, in this course, talk about 3 different experimental designs. So this is a completely randomized design. The experimental units are assigned to the treatments completely by chance. So here's a diagram. You're going to be asked to diagram these experiments. You start with your experimental units, people, objects, trees. The one example we came up with was the schools. Remember the malaria example? We take those people, objects, whatever, experimental units, we randomly assign them into however many groups we need. We give each group a treatment, and then we compare the response variable. So you're going to actually be diagramming and explaining this diagram, okay? So just a quick reminder, your treatments can be a different level of a single factor. Like, for example, with the heart medication, maybe my treatments might just be the new medication, the old medication, and the placebo. So different levels of that single, factor, or several different factors. So, or I could maybe look at, like we looked at the drug and the exercise together, and they each had 3 levels. So each of those 2 factors had 3 levels. So we would have 9 treatment groups, right? Okay, so we're going to go back and we're going to diagram 2 experiments. So the Coca-Cola example. So diagram that experiment using 20 students. Explain each phase of the diagram. Ready? So we are starting with 20 students. We're going to take those 20 students and we're going to randomly assign them to treatment groups. But how are we going to do that? This is the biggest part of the explanation. Here we go. We kind of already went through this exact same thing. I copied and pasted it, right? We label each student with a different integer from 0, 1 to 20. We go to a line of table D. We read 2-digit groups moving from left to right. The first 10 different labels between 0, 1, and 20 are the 10 students who get cola with caffeine. The remaining 10 get the caffeine-free cola. We ignored groups of digits from 21 to 99 and 0, 0. So Here's these people being split into groups, right? And then the next thing I do is I take the people in the groups and I give them their treatments, regular Coke or caffeine free. And then ultimately, they told us that the response variable was that they wanted to compare the pulse rates. So this is my diagram, and I explained each phase. I explained how I randomly assign them. There's specific numbers here. I'm specifically stating that there's 20 students, 10 students in this group, 10 students in this group. I'm, specifying that these people got the regular, these people got the caffeine, and I'm also specifying what we're comparing. Ultimately, we're comparing the pulse rates. Remember, that's the response variable. So this is your diagram along with the explanation. Now, I really fast want to go through those 4 principles of statistical design, right? So comparison was the first one. We're comparing 2 different treatments. Random assignment. We randomly assigned the 20 students to the 2 different groups, right? Control. So we try to control for the presence of other variables, the confounding variables. I don't know that we can really see that in this example. There wasn't much detail here, so I don't know that I really necessarily see any control here. Replication. I have 20 students, so in other words, I have 10 students in each group, so I replicated the experiment. In other words, I didn't just do it with one person. All right? So if you're asked to check on those 4 things, that's how you would do it. Okay, here's our big one. Ready? Heart medication example, diagramming experiments. So diagram that experiment using 900 patients. Explain each phase of the diagram. So very similar. We start with our 900 patients. We're going to randomly assign them. Remember, going all the way back, we had 9 different treatments. We had the placebo and no exercise, the placebo and low exercise, the placebo and moderate exercise, etc., etc., etc. So here's how we're gonna do this randomization. And again, just like I said to you guys with simple random sampling, this is a lot of writing. It's annoying, but yes, it all needs to be there. So we label each person with a different integer from 001 to 900. You could say a different three-digit number. Go to a line of table D, read 3-digit groups moving from left to right. The patients who correspond to the first 100 unique 3-digit numbers between 001 and 900 are going to go into group 1. So then I'm going to repeat that process until I have 100 patients in each of the 9 groups, and I'm not allowing for any repetition of the 3-digit numbers. So in other words, I'm throwing out repeats. All right? So that's my explanation of my random assignment. Here we go, we're getting crazy. So now I'm randomly assigning these 900 people. These 900 people are coming. They're being randomly assigned into these 9 groups. Notice I'm very specific. In the beginning, I labeled that there's specifically 900 patients, 100 patients in each group, right? And then each group goes on to take a treatment, and I labeled the treatments: placebo, no exercise, placebo, low exercise, placebo, moderate exercise, drug A, right? Drug B, with all the different exercise levels, right? So each treatment is labeled with the specific treatment that is being given. And then my response variable, remember we said we're going to compare the frequency or amount or whatever of heart attacks within each group. All right? So really quick, let's go through my 4 principles of statistical design. So comparison, random assignment, control, and replication. And by the way, those 4 things aren't in any particular order. You can list them in whatever order you'd like to. But comparison, so I'm comparing 9 different treatment groups here, right? So 9 different treatments. So I'm comparing, randomly assigning. So remember, random assignment tries to kind of make sure that the people, these 100 people in each group, are all mixed up. So, you have an equal amount of 50-year-old people in each group, an equal amount of people with a bad history of heart attack in each group, an equal amount of people with various different like health conditions in each group. And when I say equal, it's never going to be totally equal, but we're trying to even it out as much as possible. So reminder, just a couple reminders, that's what that randomization kind of does there. So let's go to replication, because that's always like I think the easiest one. So replication, I have 100 people or patients in each group. I'm replicating this experiment with a total of 900 patients. So remember replication, we just don't want to give each treatment to one person, because one person, we want to see what it happens over like a lot of different people, the systematic like successes or failures of these different treatments. And then last one, I think this is like always the trickiest one for some people, control. Remember, it's not the control group. Really, this would be your control group, this treatment one, because they're getting the placebo and no exercise. So treatment one would be like your control group. That's like your baseline, right? But when we talk about the principle of control, we're saying that we're controlling for like confounding variables. So remember we said that some confounding variables in this case might be like the diet, that these people are on, other supplements. So maybe, and again, so far from what I see, I would say I don't really see control. But if you're asked, like, how could you control for confounding variables, you could say something like they would all be on the same diet, they would all be on the same bedtime routine, things like that. All right? That was a lot. That's that's all I have for you. Feel free to go back, rewatch, and thanks for listening.